Hello everyone and welcome back. My name is Mr. Covalt, and in this video I'm going to be going over an introductions, acids, bases, and pH calculations. First I want to talk about the properties of acids and bases. So first, acids. Acids are usually found in fruits and juices. They commonly have a tart or sour or sharp taste. So if you've ever had fruit juices, you'll know that taste. Lemon juice, kind of sour. So that's because there's acid in there. Also, in your carbonated drinks, there's acid. So they are electrolytes, meaning that they conduct electricity. The acids will ionize in water and become ions, and that allows for the conduction of electricity through the solution. A common property is that they react with metals. They'll react with metals to form hydrogen gas. And then they're also commonly aqueous and liquids. Aqueous meaning that dissolved in water, or they're liquids. So those are the common characteristics of acids. What about bases? Bases, they tend to be found in cleaning products like Drano. They have a bitter taste instead of a sour taste. And then if you feel them, if you kind of touch your hand on them, they'll feel slippery, like kind of like soap. Soap and those detergents have a basic proper are kind of basic as well. So they have a slippery feel to them. And also, they're commonly solids. So instead of being aqueous or liquids, you'll find them in the solid form. Okay, let's talk about three different definitions of acids and bases. Okay, so let's talk about a few definitions of acids and bases. So the first definition I want to talk about is the Arrhenius definition. So according to the Arrhenius definition of acids and bases, an acid is something that makes or produces H plus ions in aqueous solutions. And base is something that makes or produces OH minus or hydroxide ions in aqueous solutions. So if you do that, if you have a substance that's going to produce H plus or OH minus, then you've got an acid or base according to the Arrhenius definition. So if we look at these examples here, so here we have HNO3. HNO3 is going to break apart or ionize into H plus and NO3 minus. You have your nitrate ion and your hydrogen plus ion. And so this would be an acid according to the Arrhenius definition because it's producing or making an H plus. So for the base, you have KOH. KOH is going to dissociate into K plus ion, your potassium ion, and your hydroxide ion, your OH minus. And so because this is producing OH minus, this is a base under the definition of the Arrhenius definition of acids and bases. So what about the Bronsted-Lowry acid and base? So according to the Bronsted-Lowry definition of an acid and a base, instead of talking about producing H plus ions, it refers to as donating a proton or H plus. We call an H plus ion a proton because that's literally what it is. So if you have a hydrogen with the electron removed, all that you have left is a proton. So here we call it donating protons. Now, donating implies that you are giving the H plus to something else. Whereas in this case here, excuse me, there's not a necessary, there's no concept of donating here. You're just giving off or producing the H plus. So for something to be an acid or a base, you have to have the H or the OH in the formula. But here, in order to be an acid or a base, you don't necessarily have to have an H plus or an OH minus in the formula. So for an acid, you're going to donate an H plus, and to be a base, you're just going to accept that H plus. So an acid and a base are going to be together, right? So if an acid is donating the proton to something, then whatever is accepting that proton from the acid is automatically going to be the base, right? So here's an example. So here you have NH3 ammonia. Ammonia is going to react with HCl, hydrochloric acid. And here the hydrochloric acid has an H. So this is an acid according to the Arrhenius definition as well. But according to the Bronsted-Lowry definition, it is also an acid because it's going to donate, excuse me, it's going to donate the H here to the NH3. So it donates the hydrogen, it gets rid of the hydrogen, and you end up with Cl minus. And then the NH3, the ammonia, is going to accept that proton from the HCl. And so it's going to become NH4 plus. So here, ammonia is a base according to the Bronsted-Lowry definition. It is not a base according to the Arrhenius definition because it is not producing OH minus. You do not see OH minus being produced here. So ammonia is a base according to the Bronsted-Lowry definition, but not according to the Arrhenius definition. So this definition is broader than the Arrhenius definition. It allows more things to be considered acids and bases that would not be allowed to be considered acids and bases under the Arrhenius definition. Now, what about the Lewis definition? So here's our third definition of acids and bases. According to the Lewis definition of acids and bases, an acid is an acceptor of an electron pairs. It accepts electron pairs. So here we're not focused on protons or H plus. We're focused on electron pairs. So an acid it accepts electron pairs, and bases donate electron pairs. So here we're talking about donating protons for acids. Here we're talking about accepting electron pairs for acids. And bases are donating electron pairs. So here is an example. So here we have ammonia again written in its Lewis dot structure. So we have NH3, and notice that it has a lone pair on the nitrogen, which is typical for nitrogen. So this is going to donate its electron pairs. So as a donator, we usually will call this an electron donor, right? So the electron donor here is your ammonia. That's your Lewis base because it's donating the electron pair. And here we have BF3, boron trifluoride. And so this is going to be the electron acceptor. It's going to accept the electrons from the nitrogen. And so here we have a Lewis acid. So the BF3 is a Lewis acid, and then they form a bond. Now, the thing I want to point out here is this BF3 is an acid according to the Lewis definition. But according to the Arrhenius and Bronsted, it is not an acid, right? So according to the Arrhenius definition, it would be an acid if it produces H plus. But here, it's not producing H plus. It doesn't have an H plus to produce, so it's not an acid according to that definition. Here, an acid donates protons, but BF doesn't have a proton or a H plus to donate, so it can't be an acid according to that definition. But according to the Lewis definition, it is an acid because it will accept an electron pair. So these definitions are even more broad than the definition of the Bronsted-Lowry type. So we can see that there is a progression here of broadening the definition of acids and bases. So the least broad or the most specific definition of your acid and base is going to be the Arrhenius. And then the next more broad definition is your Bronsted-Lowry, and the most broad definition is going to be your Lewis acid and base. So here I have a little diagram here, a Venn diagram, kind of representing or in a pictorial way what I'm saying here. So if these are all the molecules that could be acids or bases, right? So you can see that the larger circle, Lewis acids and bases encompass more than, say, the Bronsted-Lowry. So, excuse me. Sorry about that. So here you can see that the Lewis acid base definition encompasses more substances as acids and bases compared to the Bronsted-Lowry and Arrhenius. And the Bronsted-Lowry definition encompasses more than the Arrhenius. So the Arrhenius is the most specific, and it has the least that are going to fall in this category. And then the Bronsted-Lowry allows for more to be considered acids and bases. And then your Lewis encompasses more. Okay, so that is your different definitions of acids and bases. Let's talk about water now. Okay, let's talk about water. So with regard to water, water is fascinating because it can act as either an acid or a base. So here's a couple of examples. So here I have ammonia and water. In this case, ammonia can take a hydrogen from water. It'll accept the hydrogen from water. Water will donate the hydrogen H plus. So then you get NH4 ammonium, NH4 plus, and you get your hydroxide. So here, because water is donating an H plus, then that's going to be an acid, and NH3 is going to be your base. Here we have HCl and water again. In this case, the donator is going to be the HCl. So HCl donates an H plus to water. Water is now the H plus acceptor. It becomes H3O plus and Cl minus. So here water is acting as a base. So water is accepting a proton in this case, and then in this case it's donating a proton. So it can be either or, and in substances like this that can do either donating or accepting a proton, or it can be an acid or base. We call those amphoteric. Okay, so now let's talk about which type of acid or base. Let's do a little quiz here. So you can pause the video right now. Look at these. So we have HBr, LiOH, CO3 2 minus. I have it underlined. We have C6H5OH. So that one here. And then we have this one and this one. What can you identify the type of acid or base that it is? So first you need to identify whether it's an acid or base, and then you got to identify, well, what kind is it? Okay, so you can pause the video, see how well you do, and I'm going to go over this. Okay, let's get started. So the first thing here, you notice it has a hydrogen in it. And so that's going to be the giveaway that this is a hydrogen of the Arrhenius acid kind. This is going to be an acid of the Arrhenius kind. So this would be your Arrhenius acid because it can produce an H plus from the formula. Here, so let me underline this. So here, hydrogen. Here you see an OH, right? So that OH, this is your hydroxide ion. So it can give off or produce or create an OH. So this is going to be a base of the Arrhenius kind, right? So this is going to be an Arrhenius base. All right. Now, what about CO3 2 minus? So if you look at the reaction, it'll kind of give it away. So here we have CO3 2 minus. We have two H pluses here, and the H pluses are picked up by the CO3 minus, your carbonate ion, and it's going to form H2CO3, your carbonic acid. Now, because this is picking up the 2H plus, that means it's going to be a base of the Bronsted-Lowry kind. So it's a Bronsted-Lowry base. So this is going to be a Bronsted-Lowry base. So I'll write it over here. So this is your Bronsted-Lowry base. And here, if you look at the equation, you'll see that what's happening here is that this molecule is giving off this hydrogen. And so notice that it doesn't have the hydrogen there anymore. And notice that this NH2 minus now becomes NH3, so it picked up the hydrogen. So this is donating the hydrogen. This is accepting the hydrogen. The H plus, the proton, right? This is a proton donor. This is the proton acceptor. So that means that this is a Bronsted-Lowry acid. So let's label that. So this is going to be your Bronsted-Lowry acid. All right, finally we have these two. So here we have a carbon with three CH3 groups on it with a plus, no electrons here. There's no hydrogen to give away. There's no OH minus. So if we look at what's going on, it looks like we're forming a bond between the carbon and the oxygen of water. Water has a couple of electron pairs here. So it looks like we have accepting and donating electrons. So now we're talking about Lewis acids and bases. And so in this case, we're going to have this one that's donating. It looks like this one's going to donate electron pair. So this is going to be the Lewis acid. So donating. Where are we going here? Yeah. Lewis base. Okay, here we go. So we're going to have Lewis. Okay, so let's see. Do Lewis here. Okay, this is going to be our Lewis base. So water is our Lewis base, and this is going to be our Lewis acid. There we go. So the Lewis base is your electron pair donor. So it's going to donate the electron pair, and then your Lewis acid is going to accept the electron pair, and that forms the bond. So that, if you got that right, then good job, kudos to you. If you didn't get it right, hopefully you found your mistake, and then you won't make that mistake again. And hopefully this clarifies how to identify whether you have an Arrhenius acid or base, or Bronsted-Lowry acid or base, or a Arrhenius acid or base. Okay, so now let's go on and talk about conjugates. Okay, let's talk about conjugate acids and bases. So when you have an acid and a base react, they're going to form what are called conjugate acids and bases. So the acid is going to turn into the conjugate base. So acids are going to turn into their conjugate bases once they have lost their proton or their H plus. Bases are the opposite. They're going to turn into their conjugate acids once they have gained a proton. So what does that mean? So here's an example of a reaction. Here I have NH3 ammonia. So NH3 reacts with HBr, hydrobromic acid, and that's going to form NH4 plus, which is ammonium, and then you have Br minus left over. So the acids are always identified, the acids and bases are always identified by the reactant side. They're never going to be on the products. The conjugate acids and bases are always going to be on the product side. So here's where you're going to find your conjugate acid and base. Here is where you're going to find your acid and base. So don't confuse that. So you're not going to identify these as conjugate acid and base. So never do that. So conjugates are on this side, the acids and bases are on this side. And so you can identify your conjugate acid by the fact that they differ by one proton. So here you have NH3. NH3 is going to pick up a hydrogen from HBr and it forms NH4 plus. So you can see that this is NH4 plus, and so you can see that they are related to each other by one hydrogen. This one is gaining the hydrogen to get NH4 plus. This is losing the hydrogen to get the NH3. So the way to understand the conjugate acid and conjugate base is to think of the reverse reaction. If this was to go this way, if it was to go in reverse, then what would be the acid and base on this side? Well, this would act as the acid because then this would have to donate a hydrogen to your Br to get HBr back and your NH3 back. So that's what we mean by conjugate acid base. So if this is in equilibrium, then these would be working this way in order to reproduce your acid and base on this side. So that's why we are calling these a conjugate acid, because if it goes this way, this is acting as an acid and this is acting as a base. But we don't call it acid and base, we call them the conjugate acid and base. And so again, the base and the conjugate acid are related to each other by the transferring of a proton, and then the acid and conjugate base are also related by the transferring of a proton. So that's how you can identify which one belongs to which one is which. So a few tips for finding each. First, find the acid. That's usually the easiest, so HBr is the acid here, find that. And then find its conjugate base, which is the part that's left over after it's donated your hydrogen. So here, HBr donates hydrogen to NH3, and what's left? Br minus. So that is your conjugate base for this acid. And then you do the same thing for the base. The other one has to be the base. So this is your base. So the other one is linked to the conjugate acid on this side, again, by the transferring of a proton. So this one is gaining the proton to get your NH4 plus. Okay, so let's do a little practice. So you can pause the video, and what I want you to do is, for both of these equations, identify which one is the acid, which one's the base, and what is the conjugate and acid, conjugate base and conjugate acid of those. So go ahead and pause the video, and then restart it when you are ready. Okay, so here, so the first one I have HF and I have SO3 2 minus. I see that there's a hydrogen here, so I'm going to identify this as the acid. So here we have the acid on this side. And you can see here that if you're like this one, you have F minus, it lost the H. So also that indicates that this must be the acid. So here we have the acid. And then SO3 2 minus must be the base. And you can see over here that it accepts the hydrogen because now we have HSO3 on this side. So then, if this is the acid, then the conjugate base is going to be what's left over. It's going to differ by an H. So here we have HF, here we have F. So this is going to be the conjugate base. CB for conjugate base. So why? Because if we go backwards, we're going to go from F minus to HF. So this must have picked up a hydrogen, so that's making that a base. So it picked up the hydrogen from here to reproduce SO3, which means that this base has to be connected with this conjugate acid. So this is the conjugate acid here. Okay, what about here? So here we have water reacting with CH3COOH, acetic acid. And so we got to identify the acid. Well, I just said it was an acid. How do I know this is an acid? Because here you have H. So that H is going to go away. COOH is a common grouping. So if you see I have a COH, this H is an acidic H, it will give off. And you can also see over here that it's gone. So that's a dead giveaway that this is the acid. So we have the acid, and that means water must be acting as the base. And we can see that over here that H3O plus, so water must have picked up a hydrogen. So it's the base. So again, to get the conjugate base of this acid, we're looking for what's left over when this is donated, which is your CH3COO minus. So this is your conjugate base. And then water, you have the base. Well, this one must be the conjugate acid because that's left over. But you can tell that because the base picks up an H from the acid, and now you get CH3. So this is your conjugate base. So the conjugate base and the the conjugate base and the acid. Oops, did I mess it up? Base. Oops, this should be conjugate acid. Why didn't someone say something to me? Okay, I caught my mistake. So here we have the base and we have the conjugate acid. What am I doing? We have acid, conjugate base. I changed the wrong one. Acid, conjugate base, and this is the conjugate acid. Here we go. Good. Okay, finally. Okay, so we have base and then the conjugate acid, and you can tell these go together because they differ by the transfer of a proton. And you can see that this is the acid and this is the conjugate base because they differ by the transfer of a proton. So there you go. So that's how you identify the acid conjugate base pair of each of your substances, or the base and conjugate acid pair of your substances. So I know I made a mistake, but I caught it. So you can catch that too if you know what you're looking for. So let's go ahead and then now talk about some other things related to acids and bases, like pH scales. Okay, let's talk about pH scales and pOH scales. So what is a pH scale? It's a scale that lets us measure the relative power of hydronium ions in a solution. So how, basically it tells us how acidic or basic a solution is. Now, what's a hydronium ion? A hydronium ion is your H3O plus, which we also refer to as H plus. H plus really doesn't exist in solution. It only exists as H plus connected to water gives us our H3O plus, which is the hydronium ion. And so when we're looking at our pH scale, here's our pH scale. And our pH scale goes from 0 to 14. And our pH scale is a measure of our hydronium ion. It says power. Power is referring to the exponent on the concentration of our H plus ions. So here we have concentration of H plus, and you'll notice that the pH is the power, but notice it's the opposite sign. So 0, 1, 2. So here is our concentration of H plus. It's decreasing, and if we look at the pH numbers, it's increasing. So here we have acidic, so that means we have more H plus. So if you have an acidic substance, that means you have more H plus compared to a basic substance, which has less H plus in solution. So this is going to be a measure of how much H plus we have in a solution. So the larger the pH number, the smaller the amount of H plus we have in solution. And so we can also look at this from the pOH scale. The pOH scale is the opposite, and we're looking at the OH minus concentration. So it's the opposite of our pH scale. So the pOH scale is referencing a concentration of our OH minus in solution. So again, we can see this is 10 to the negative 14 and 14, and so on.